And we're back, and let's start with median. So I'm going to make a triangle here, and let's just use a red triangle. So I make a red triangle, and median saying that I'm going to take the area, split this in half. Let me split this in half, and I'll take the middle part and have this go to the opposite side. And once again, I'm going to have split this portion, and I'm going to have this go to the opposite side. Now you notice this is different from a perpendicular bisector. The difference is both of them are starting in the same place. They're both starting in the middle of the area, but however, the point of a median is to go to the opposite side. However, the point of an angle bisector is to be a bisecting or perpendicular bisector is to be bisecting at a perpendicular. So it has to bisect at 90 degrees right in the middle. So that doesn't necessarily mean it's going to hit this. It just means that that's what it's going to try to do. So let's make the third line here right here, and let's see if it corrected. So I would seem to be a little off. Of course, I'm estimating this. However, let's just make this right here the points where all the three medians meet. This point of concurrency is called a centroid. What is significant about the centroid? Well, if I took this line right here, I could tell you that the point of from the top to the centroid will be 2/3 of the entire line, and from here, the bottom right here, this will be 1/3. So if I were to tell you that the entire line is, for instance, 12 from A to E, and let's put a C in the middle. If I told you that line segment AE is equal to 12, you'd be able to tell me that line segment AE is 2/3 of that. Excuse me, not AE. You'll tell me that line segment AC is 2/3 of that, so therefore 8. And then you'll also be able to tell me that line segment CE is 1/3 of that, fourth. So if I give you any one of those three informations using a centroid, you'll be able to find out the other two. And let's go on to the last one. The last one is an altitude. And remember, this is what we do to find out the area of a triangle. You find the altitude. So an altitude works is you take a line from here that goes straight down. Let me see if I can. All right. So you find a point, go straight down 90 degrees, right? Now this may seem easy when we have an acute triangle. Let's try it out with an obtuse triangle, however. Or let's try a right triangle. So an altitude, in this case, would be where it hits at 90 degrees. So for instance, this point here, we're going to see where it hits this line here at 90 degrees. So if I were to estimate, of course, which I have been doing, it'd probably be right around here. Right around here. So just say with geometry, you have to assume I'm right just because I put that there. However, we got to do this with the other points too. So for over here, we got to find out where we'll hit this side at 90 degrees. And since it's a right triangle, we know that for this is going to be right here. And for this side, we're going to see where it's going to hit the already pink version at 90 degrees. So we're going to also, let's make it green this time, know that's going to hit right here. So for a right triangle, we know that the point of concurrency is right there. It's on the line. For a right triangle, it will be on one of the three sides. And once again, this area is called the orthocenter. Now it gets a little confusing with obtuse triangles. With obtuse triangles, you have a triangle like this, and now you're trying to find a point of concurrency. So in here, let me flip this around because it usually makes it easier when we flip it around like this. We have to find out where the points are 90 degrees. So over here, we're going to take a blue marker, and we're trying to find out where this will hit this pink line at 90 degrees. And so it will probably be around out here somewhere. It finally hit this line. If you were to extend this line, it hit it right here at 90 degrees. Similar with this line, if you were to find out where it hits, let's see, if you find out where it hits this point, will hit this line. Well, you have to extend this line now, and you'll see that with the green, it'll probably hit somewhere around here at 90 degrees. And then for the last point right here, this will be a little easier. I will be using the black marker this time. It's gonna probably hit, I hope my triangle doesn't move, around there. So if I were to extend these, and what should essentially happen is, perhaps I think my blue line might be off, and that's what's causing this problem. Um, But what should happen is that they should all be meeting at a point. So it's probably more like this, and they're probably meeting out here. So for an obtuse angle, they're way outside the triangle. The original triangle we started with, let me highlight in green, is this. This is the original triangle we started with. Now what's happening is the orthocenter is way out here. So that's how it happens with an obtuse triangle. So let's go over a few more information. So any triangle, there's a few things you need to know. That if I gave you the sides of the triangle, A, B, and C, two of the sides cannot be greater than the third side. So if I were to add any two of these sides, let's say A and B will have to be less than C, not even less than equal to, less than C. And the way this works is, if you think about it, if I had a triangle and I had a line, let's say if there's a value of 8, and I say I had two more sides that were 4 and 4, well, that's not gonna work, because even if I try to do just a little angle, they would have to be greater than 4 to get that distance. So that's what it's saying, that if you add up any two sides of a triangle, it has to be greater than the third side. So ideally, I can give you a triangle, and I can tell you this triangle is not drawn to scale. However, the sides in this triangle are, let's say, 4 and 15. And I have to tell you what is the least and most that this size can be. So first you have to assume that for the least it could be, that this is going to be the largest size. The 15 is going to be the largest size. So you're going to say 4 plus what number has to give me more than 15? So in this case, we say 4 plus, let's call this B, has to be greater than 15. So B has to be greater than 11. The second thing we have to assume is maybe there's a side even bigger than both of these. Maybe B is the biggest side. So in that case, you would add up 4 and 15 plus 15, and they have to be greater than B. So now we're going to find out 19. So B has to be less than 19. So in this case, I gave you this possible scenario, and we don't know what B is, but I'm telling you that B has to be somewhere between 11 and 19. So it has to be greater than 11 and less than 19. So that's what this side is telling you. Another concept about this is, let's say I have two triangles and they're congruent, and the sides are congruent. So let's say this triangle and this triangle. And let's say the sides are congruent, and I told you that this triangle has, let's say, 50 degrees, and this triangle is, for instance, 60 degrees. And I ask you about the side I'm going to be highlighting in pink now. And I say, which side is longer? And you're going to tell me, because you already know this, that the side that has the longest here is going to have the longest side over here. However, in this case, because this triangle has 60 degrees here, this side, which we'll call side A, has to be longer than this side B over here. These are going to be congruent. They're going to be similar to each other. It's a side angle side principle, but we gave them different angles here. And so we're saying, based off this and the fact that this side and the sides next to it are congruent to each other, we're going to say, based off all this information, that A is going to have to be bigger than side B, because A has across from it 60 degrees and B has across from it 50. And that's the hinge theorem. And that concludes everything, alhamdulillah.